Welcome to the first of 3 presentations which provide an introduction to mine-to-mill. The presentations are not designed to provide a blueprint to do a successful mine-to-mill, but rather provide the background, the understanding and the tools to help execute a successful mine-to-mill. The 3 parts cover the influence of feed size on AG and SAG milling. The second part is an introduction to blasting, aimed very much at minerals processors. And last, the presentation discusses how we can change the AG-SAG feed size through manipulating blasting. Let's first of all look at an historical perspective. And if we go back prior to the rise of AG and SAG mills, multi-stage crushing and milling circuits were the norm, and these circuits were relatively insensitive to the primary crusher product. Now, as a result, mining KPIs at that time were driven largely by the minimum cost per cubic metre of broken rock delivered to the primary crusher, and as such, size distribution requirements really only needed to be limited to being able to fit rock into the primary crusher. As a result, most typical primary crusher products were relatively coarse. As AG and SAG mill circuits started to become more and more popular in the 1970s and the 1980s, experience started to show that they tended to be very much less stable than the more traditional multi-stage crushing and milling circuits, and feed size variations were seen to be the cause of this. Now, the then conventional wisdom was that AG and SAG mills needed coarse feed to supply sufficient grinding media. So with that requirement, a coarse primary crusher product, which had historically been provided to the multi-stage crushing and milling circuits, didn't appear anyway to provide any conflict between the prevailing mining KPIs and what experts at the time thought would be the best AG and SAG feed size requirement. In the early 1990s, however, views with regard to AG and SAG mill feed size started to change, and one very dramatic and very successful installation at Kidston showed very, very clearly that a finer feed could provide significantly higher throughputs. Now, in the case of Kidston, that was achieved through secondary crushing, and I put there a paper that was published authored by Needham and Folland, which discusses the expansion of that Kidston gold mine back in 1994. Just out of interest, it was very much the brainchild of Graham Folland. Placer owned Kidston at that time, and they were sponsors of the Amira JKMRC P9 program, and we had developed at that stage the variable rates SAG mill model, and Graham and his team explored the use of that model and looking at what, from a simulation viewpoint, making the feed to their existing SAG mill circuit would do to the throughput. Kidston was nearing the end of its life, or at least the higher grade life of the mine, and they were looking at ways of dramatically increasing throughput so that they could treat lower grade ore and continue to make Kidston money. It was a very, very successful expansion, and it went against very many people's ideas at the time of what was appropriate for successful SAG milling. At about the same time, at the JKMRC, the mining and minerals processing programs had matured to the point where Don McKee, who was the director, started to consider whether we could influence SAG mill feed through manipulation of the ROM, which in turn, of course, was manipulated by blasting. And there are two papers there, one of the first papers of their kind, which explored that relationship between fragmentation in the pit and comminution circuit throughput. And out of that came the first mine to mill program. That was in 1996. Very much the brainchild of Don McKee. He was the principal driver of that. And that first research program was co-led by myself and Andrew Scott. So in this three-part series, we're going to pick our way through that historical perspective and expand on various sections of it. And the first part, we're going to look at the influence that feed size has on ag and SAG milling. This graph has been taken from the paper which is detailed at the bottom of the slide here, the optimization of the Cady Hill SAG mill circuit. Cady Hill was the first circuit to have a 40-foot diameter mill, and this paper was presented in the SAG Conference 2001. There are a number of papers about the Cady Hill circuit, both the design and subsequent optimization. And this graph has been reproduced a number of times by various authors over the years as a good example of the influence that SAG feed size has on the performance of a SAG mill. There are lots of scatter in the data. It is production data. The SAG feed size F80 has come from image analysis, and as a result one sees this scatter. Nevertheless, the trend is very apparent. Throughput goes down as the SAG feed size F80 goes up, and that is in response to the specific energy which goes up as the SAG feed size goes up. The SAG conference volumes are a very rich source of all sorts of information. They're a particularly rich source of information from a very large number of plants around the world that have experimented with and published information on changing the F80 and what it has done to the SAG mill performance. And in all cases, the trends are exactly the same as we saw in that previous slide. And I've been through a lot of those published data and come up with this very simple rule of thumb that will enable you to get some estimate of what to expect on your plant if you were to reduce your F80. And the rule of thumb basically is that the percentage reduction in your current SAG mill kilowatt hours per tonne will be approximately half the percentage reduction that you can make in your existing F80. So let's take an example. If my plant had an F80 of 100 millimeters and I decided to put something in place, whether it's secondary crushing or blasting, and I was able to reduce that 100 millimeters to 80 millimeters, then that would be a reduction in the F80 of 20%. Now let's say that our existing SAG mill specific energy when we're treating an F80 of 100 millimeters is 10 kilowatt hours per tonne. So our expected reduction in specific energy is half of that 20%, or 10% reduction. So a 10% reduction on 10 kilowatt hours per tonne is 1 kilowatt hours per tonne. Therefore, our new specific energy when our SAG mill is treating an F80 of 18 millimeters is expected to be approximately 9 kilowatt hours per tonne. A word of warning, however, and it's to do with the use of single point descriptors of size distributions. And I've talked about this before in the masterclasses that some of you may have looked at. Distribution is important, and it is particularly important when we look at feed sizes to SAG mills. Here we have two distributions. These are real distributions. They come from a plant that I did some work on, and you can see here the blue line has a smaller F80 than the orange distribution, but you can see they have different shapes. And in this particular case, the size distribution with the larger F80 actually gave a higher throughput than the distribution with the lower F80. And the reason for that is distribution, and specifically it's because the F80 at 130 millimeters, and they're the blue histograms there, you can see they have more fines, and in this case I've defined fines as minus 9.5 millimeters, and that was approximately the aperture of the discharge screen of the SAG mill, and also has significantly less what I've called intermediate size material in the range 31 to 100 millimeters. And you can see the purple histogram for that particular size fraction has almost 45% of the entire distribution is in that basket, compared to the F80 at 130 millimeters, which is down at about 27%. Now, that size fraction is in the so-called critical size class, and you may have heard that term used before, being used to describe material in the SAG mill that the SAG mill finds quite difficult to break down, and any build-up of that tends to limit the throughput. Well, not only build-up, but of course if you feed a SAG mill in the first instance with an excessive amount of that material, then you're already starting on the wrong foot, and it effectively simply goes downhill after that. So be aware, and this is particularly relevant when you're trying to reduce your feed size through blasting as opposed to secondary crushing. Secondary crushing typically will reduce the entire distribution in a fairly systematic manner. Blasting is perhaps a little less able to be predicted and controlled, and sometimes you think maybe you are doing the right thing by blasting in a certain way to get a finer feed to the SAG mill, and inadvertently you may well end up by generating larger amounts of intermediate material than expected and actually make the throughput situation worse. Here is another very good example of the influence of feed size distribution on SAG mill throughput. And the data in this graph have been taken from the paper that you can see I put at the bottom of this slide. It's a paper that myself and Walter Valeri put together back in 2001 for the SAG Mill conference. And these two distributions come from one plant which has two feeder lines, each feeder line feeding a separate SAG Mill 1 and SAG Mill 2. But in this case, the feeder lines were installed underneath the stockpile asymmetrically. And because of the inherent segregation that occurs in stockpiles, the result of this was that one feeder always fed a coarser distribution than the other feeder. And you can see that very clearly in SAG Mill 2's feed. They're the blue lines and points, which is very much coarser. Even though it has the same P80, the distribution is very different. And if you recall one of those earlier slides that I showed you where we discussed the varying amounts of intermediate size material and the influence that that had on throughput, we can see here that SAG Mill 2's feed has much more of that intermediate size material and much less fines than SAG Mill 1. And as a result on this plant, the finer feed, which always went to SAG Mill 1, gave consistently 50% higher throughput than the coarser distribution. While we're on the subject of stockpiles and stockpile segregation, I collected these data many years ago at a plant that had a stockpile level indicator, and I was able to collect these data from a period where the primary crusher had to go down for maintenance, and so the SAG mill circuit was being fed from the stockpile. And as time went on, of course, the stockpile level dropped, and because of segregation in the stockpile, that gave a change in the F80 to the SAG mill circuit. This particular plant had an image analysis system, so it was able to monitor that change in the F80. And you can see there the blue line shows the stockpile level. And initially it's relatively constant, and as a result you can see the SAG mill kilowatt hours per tonne, that's the purple triangles, is reasonably steady, and the F80 also reasonably steady. If you look at the time period number 3, that corresponds to when the primary crusher had to be taken offline and the stockpile level starts to go down. Initially, not much change in the F80, but then by time period 4, things start to change. F80 starts to ramp up, and straight away the SAG mill kilowatt hours per tonne goes up, and there would have been a corresponding reduction in the tonnes per hour. And you can see from time period 4 right the way through till time period 8, the specific energy goes up from 9 to 12. That's a 33% increase in the SAG kilowatt hours per tonne, a really quite significant increase, and would have caused, of course, a significant change in the tonnes per hour. So another good example of feed size and what feed size does, this time of course caused by the stockpile. When you're at the design stage of a new SAG mill circuit, obviously the subject of what will be the SAG mill F80 will be discussed. And I don't know how many projects I've been on over the years, and I've seen the specification that's been put out by, whether it's the engineers or the equipment manufacturers or whatever, that the SAG mill feed size is going to be 152 millimeters. Now 152 millimeters is 6 inches, and certainly there are large, or at least there were large numbers of engineers that thought that that was a reasonable number to expect for a SAG mill feed. And then when you have a look at the equipment manufacturers, the primary crusher manufacturers' tables, and you look at the relationships they have between closed side setting and the crusher product, then 152 millimeters 6 inches can be achieved by a closed side setting of round about 6 inches, and everybody, well, at least some people, seem to be quite happy with that. In practice, of course, it's nonsense, and the reason I say that is that that graph in the figure is a histogram. Those blue blocks are a histogram, and each of those blocks represents a certain size class, and the data that have been used to generate that histogram come from over 100 operating SAG mills around the world, and you can see that the mode is between 85 and 110 millimeters. So on average, the SAG mill feed size is under 100 millimeters. And if you look at that magical 152 millimeters, it's in the size class, not quite on the far right, but certainly one of the right-hand size classes. There are not many SAG mills around the world that have such a large SAG mill F80. So why is it then that we have seen before these relatively large SAG mill F80s being specified for SAG mill circuits, whereas in actual practice we see much smaller ones? And in particular, if we look at crusher manufacturers' tables at the sort of P80s that they are predicting we should get from the closed side settings that we're operating with, and yet we don't see those sizes being fed to our SAG mills, there would appear to be some sort of disconnect. Now, before I move on, of course, one of the reasons why some SAG mill feed sizes are bigger than others, it's not just got to do with closed side setting. There is a definite correlation between the hardness, the competence of the rock, and the SAG mill feed size. And that orange line is the correlation from that large database between the DWI, which comes from the SMC test, and the SAG mill F80. And what it clearly shows is that on average, the harder the rock, then the coarser the SAG mill feed will be. So let's have a look a bit more closely at what appears to be a disconnect between the primary crusher product P80 and the SAG mill feed F80. And to do that, we're going to have a look at some data that's mostly being provided by Dr. Walter Valeri and his team at Hatch. And I would like to acknowledge their contribution and generosity at being able to use these data. What this graph shows is the crusher product P80 along the x-axis that Dr. Valeri and his team have measured at a number of different sites, plotted against on the y-axis the SAG mill feed F80 that they also measured on the same sites. Now you can see it's correlated, and if you look up on the right hand side there, the correlation is quite high, and the equation, simple linear equation, is that the SAG mill feed F80 is approximately 80% on average of the crusher product P80. Now you might be thinking, isn't the primary crusher product the same stream as the SAG mill feed? And the answer is no, because in between the primary crusher product and the SAG mill feed is the stockpile. And if you take all of Dr. Valeri's size distribution data that he provided with me and average all the stockpile feeds and stockpile products. So remember, stockpile feed is the primary crusher product. Stockpile product is the SAG mill feed. And we compare those distributions. You can see from this graph the stockpile feed, the blue lines, compared to the stockpile product, which is the orange line, they are significantly different. The stockpile product, which is the SAG mill feed, is finer than the stockpile feed, which is the primary crusher product. So what's going on? Well, stockpiles can be up to and over, in fact, 40 meters high. If you do some very simple calculations, then the specific potential energy of a rock 40 meters off the ground is about 0.1 kilowatt hours per ton. Now you might think, well, that's nothing, don't even need to think about that. But if you consider that the net specific energy of a crusher, which is taking a feed F80 of about 250 millimeters and reducing it down to 125, so it's basically halving the F80, it would use, for an average hardness rock, something like 0.1 kilowatt hours per ton. So we're led to the conclusion that stockpiles are in fact comminutors. To some of you, this might come as a surprise. To others, possibly not. Certainly if you've had any experience in iron ore production, and I mean specifically direct shipped ore, DSO, those producers are well aware of what size reduction stockpiles, transfer chutes in conveyors, bins, what size reduction they all do. And the reason they know about this subject and are quite well aware of the influence is that with DSO ores, these are very high grade ores that are effectively dug up and shipped to the blast furnace. The value of that product is higher when it is in lump form than in fines form. And most deposits are rated in terms of their lump to fines ratio, and one hopes, if one is a producer, that one has the highest lump to fines ratio that you can, because it maximizes the value of your product. Now, along the same lines, you need to then consider that once you've excavated your material from the mine, you've got to consider what happens when you handle it, because you want to reduce the amount of degradation that is caused by that lump, so that by the time it gets to the ship or it's offloaded the ship at the other end, its lump ratio hasn't reduced significantly. Now it transpires that you can relatively easily put together a model which will predict the effect, the comminution effect that stockpile will have using power-based techniques. And this is the equation that I've put together, and it will ultimately appear as one of the tools on the SMC testing website. Of course, you're welcome to use this equation straight away now if you want to code up your own Excel spreadsheet. And the equation effectively uses the standard Morel equation, and in this case we're looking at predicting the stockpile comminution specific energy using the MIC, P80, which is the product of the stockpile, and F80 is the feed. Now this term here can be obtained directly from the specific potential energy, which can be calculated from the stockpile height. So you know this term. You know this term here because it's the primary crusher product. You know this term here because you've done an SMC test. So you can, by rearranging that equation, work out what the P80 is. And that's what that tool will do for you. And the assumption is that the specific potential energy is converted into stockpile comminution energy. Impact. It is specifically assumed, and we'll talk about this in a minute, that the energy is converted to impact size reduction. This is how well the model worked in predicting the stockpile product P80, and by and large I'm quite pleased with how accurate it's turned out to be. We had to make the assumption that the stockpiles were half full. Walter and his team, when they were doing their surveys, were not interested in stockpile height. There's no reason why they should be. So that information wasn't collected. So we didn't have that information. So we had to make that assumption. And using that assumption, the predictive accuracy is quite good. There is at least one data point, this one down here, where I was really not too happy with its predicted stockpile P80 compared to what was actually measured in practice. And there's something else going on there, and that's something I want to explore with you in the next couple of slides. And when we look at that one data point in particular where the model is not as good as I wanted to, we see something really quite interesting when we compare the shape of the stockpile feed to the stockpile product. Because way up at the coarse end here, we can see there's been almost no change whatsoever in the size distribution. But as we get to the finer end, we see a significant divergence between the stockpile feed and the stockpile product. Basically, in this case, a lot of fines has been produced by the stockpile. And I think what's going on here is that we have a significant amount of abrasion-type size reduction taking place. Now compare that previous slide, which I think signifies abrasion-type size reduction, to this information here, these two distributions that come from a stockpile where more impact type size reduction takes place. And you can see a very different transformation from the stockpile feed to the stockpile product. Largely, it's a parallel shift in log-log space from stockpile feed to stockpile product. So, what's going on in the stockpile with respect to size reduction? Well, the conditions for comminution, or at least two conditions for comminution, are that you need, one, an applied force, and two, you need relative motion. What do I mean by that? Well, let's look at impact and abrasion. If we look at impact, and in this case, here we have a rock impacting another rock, we have relative motion in that this rock is moving relative to this rock here, which is stationary. And there is an applied force. In this case, the force is being applied and supplied by the movement of this rock. Now let's look at abrasion. And abrasion typically is where there is relative motion in this direction and that direction, and an applied force is being subjected through this line here. So if we consider our stockpile, This sort of condition here, impact, would be when a rock falls from the head pulley of the feed conveyor. A rock falls from there down onto the stockpile the top of the stockpile, some meters below it. In other words, a stockpile which is not full. In this case here with an abrasion, you can consider that this sort of motion and this sort of these sorts of conditions are being found by rocks lower down in the stockpile as the particles shuffle their way down, as the stockpile is being drawn down, going to the feeder. And the force here is being provided by all the rocks stacked on top of these and providing that downward force. So typically this sort of size reduction will take place in a full stockpile. Now, in practice, of course, both these types of size reduction will be taking place. In the extreme, if the stockpile were to be empty, all of the size reduction would be by impact. In the other extreme, with a full stockpile, completely full, all of the size reduction would be caused through abrasion. Now, the model I spoke of that will ultimately go on the SMC testing website is a power-based equation, so it really can only deal with changes in the 80% passing size, and it effectively is an impact-based model. It is possible, and it's really not that difficult, to also develop, and that's what we've done, a simulation model using the JK SimMet degradation model that sits in a standard JK simulator. And the trick is to using that to accurately predict the stockpile is to recognize the fact that abrasion breakage looks quite different to impact breakage, and we encapsulate those shapes of those curves in what we call the appearance function. And those of you who looked at the modelling masterclass, I talked about appearance functions. They are size distributions, and here we can see a typical impact appearance function, that's the orange line, compared to a typical abrasion appearance function. And if you know what those appearance functions are, you can put together a fairly simple energy-based model that transforms the stockpile feed into a stockpile product. And depending on whether the stockpile is half full, a quarter full, or completely full, you can weight the amount of each of those appearance functions that are necessary for the simulation to be accurate. So if we revisit that one data point, if you remember, I talked about earlier that the power-based model was not very good at predicting. And to summarize, I think what was going on at that one particular site was that the stockpile was running full, almost completely full. And so when we looked at the stockpile product compared to the stockpile feed, the F80 had hardly changed, hadn't changed at all, but we did see a significant change at the fine end. And that's because if all these ideas are correct, then with the stockpile running full, 100% of the size reduction would have been due to abrasion type comminution. So with our JK SimMet simulator, energy-based simulator, using an abrasion style appearance function and putting in the right amount of energy associated with the height of that full stockpile, then what you see before you now, the red dotted lines, is the predicted distribution versus the measured one. And it actually looks like I've fiddled it, and I assure you I haven't. That's basically what popped out. Probably a bit of luck. Normally one's never as lucky as this, and it is only one data set. I wish I had a lot more to be able to test it out further, but at this stage it certainly would support the theory that when you do run stockpiles full, you get a different type of influence on the SAG mill feed, which is not picked up by F80. Nevertheless, it would still help with increasing the SAG mill feed rate because it's giving more fines, and those fines will simply go straight through the SAG mill without the SAG mill hardly noticing them. So you will get an increase in throughput, and quite likely it might be of a similar magnitude to the sort of increase in feed size that one's likely to get if, say, the stockpile was empty and all the size reduction was purely impact. So to finish off, is reducing feed size a panacea? Well, certainly if you reduce the feed size to a SAG mill in open circuit, and by open circuit I mean those that are closed with trommels or a coarse screen, and they can have a pebble crusher or not, that's not relevant to this particular part of the discussion. So those sorts of circuits, there is no doubt that if you reduce the feed size, you will increase the throughput. However, as you increase the throughput, the SAG mill product size will become coarser, and the ball mill will therefore have to do more work. It will have to do more work because you're increasing the throughput, but it'll have to do even more work because the throughput that's coming through to the ball mills will be of a coarser size. And if you don't have sufficient ball mill capacity to produce the grind that you want, then you will have to accept a coarser grind. Now, that's fine for SAG mills, but what about AG mills? Well, AG mills are very different, and AG mills, if their feed size is too coarse, that is not good, and if it is too fine, that's not good either. And if you think of rocks as being grinding media, and then think, okay, let's think about balls and substitute balls for rocks. If I said to you, would you run a SAG mill with 200mm balls? You would probably say, well, no, I don't think that's a very good idea. And that would be the equivalent of feeding an AG mill with far too coarse material. In a similar vein, you probably would think that running a SAG mill with 50mm balls would be quite a silly idea, and I would agree with you. And that would be the equivalent of running an AG mill with relatively fine feed. So AG mills need something in between. They need a nice graded size distribution, and it's very, very difficult to find what that distribution will be. Certainly if one looks at the size distribution to AG mills as we did right at the very beginning, if you remember that graph I showed you of the plant, which had the two distributions, the one with the coarser F80 was actually worse because of the amount of intermediate size material that was there. One thing you can say with AG mills, that if you've got a reasonable amount of coarser material and a reasonable amount of fine material, and as small amount of intermediate material as you possibly can get away with, you're likely to have a distribution which is really quite good. And last but not least, if we look at single stage mills, it's really quite difficult to work out what the optimum feed size is for that, because don't forget, with a single stage mill you're trying to do ball mill type work in there as well, where you need finer media for that, just as with ball mills need finer media, but you still obviously also need some coarser media as well. What I can say with single stage mills, definitely finer is not necessarily better, and one needs to be very, very, very careful with single stage mills about thinking, yes, I'll just put a secondary crusher in it and I'll get more throughput. Almost certainly that will not be the case, so beware. So that's the end of part 1 of this 3-part series, and if you would like to continue with this series, then the next one is an introduction to blasting.